Hello everyone, myself Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So today we are starting Unit 5, that is Stress Analysis of Aircraft Components, in which we are going to see mainly about the major components, that is wing and fuselage. So in the previous unit we've seen the structure idealization, in which we considered wing, fuselage, and also we have seen how the bending, shear and torsional loads that will impact the particular components, and we have seen the idealization also to solve the problems. And then we are moving on to this unit, the stress analysis of aircraft components, that is wings and fuselage. And in this we are seeing the first module, that we are seeing the wing spars and box beams. So the learning outcomes in this module are, so coming to here, stress analysis of aircraft components, wing and fuselage. So wing spars and box beams. So spars, so usually a normal commercial transport aircraft, it will have two spars, front spar as well as rear spar. Usually the front spar is located around 10 to 15% of the card, and then the rear spar is located around 60 to 70% of the card, depending upon the requirement, and the rest of the portion can be made available for incorporating ailerons or high lift devices, etc. So now we are going to extend analysis to actual aircraft components. So whatever we studied from Unit 1 to Unit 4, now we are going to extend the analysis to the actual aircraft components, including wing and fuselage. And presently we are seeing about wing spars and box beams. So we shall investigate the analysis of fuselage, wings, wing frame, fuselage frames and wing ribs, and consider the effect of cutouts in wings and fuselage. So the major aircraft structural components such as wings and fuselage are usually tapered along their lengths to improve the structural efficiency. So therefore, thus the wing sections are reduced both in chordwise direction as well as in depth, that is along the wingspan towards the tip, and the fuselage sections aft of the passenger cabin taper to provide a more efficient aerodynamic as well as structural shape. So usually both wings and fuselage, and that will be provided with taper in chordwise as well as spanwise direction, so that we can improve the aerodynamic efficiency as well as the structural efficiency, and then they give much more better results than the without taper cased wing as well as the fuselage. So the analysis of open and closed section beams presented in previous chapters assumes that the beam sections are uniform, but the effect of taper on the prediction of the direct stresses produced by bending is minimal if the taper is small and the section properties are calculated at the particular section being considered. On the other hand, the calculation of shear stresses in beam webs can be significantly affected by taper. So therefore, let's see the analysis of these taper by considering one example, tapered wing spar example here, and let us look into this diagram. So now we considered one tapered wing spar, and in which you can see this is the upper flange and this is the lower flange, and it is connected by thin web. And let's look into this. The SY is the vertical shear load that is applied like this, and MX is the bending moment applied in this direction. And let us assume P1 and P2 are nothing but the flange loads, that is in upper flange the load is P1, and in the lower flange let us assume the load as P2. Now this P1 and P2 are resolved into the two components. One is a horizontal component, other one is a vertical component. So you can consider PZ1 and PY1 are the horizontal and vertical components of the axial load P1, and whereas PZ2 and PY2 are nothing but the horizontal and vertical components of axial load P2 in the lower flange, and you can give the numbering also for 1 and 2. And let us assume that we considered one small element of width, that is delta Z, and now since the total depth of the beam you can consider it as H. Now since we are looking at about the taper, now let's try to write the taper on the upper flange, and from the horizontal axis that is taken as delta Y1 depth, we provided taper on the upper flange, And similarly on the lower flange we provided a depth of delta y2 from here to here, that is delta y2, that is a depth we considered for the tapered wing spar. So consider the simple case of a beam, for example a wing spar positioned in the XYZ plane and comprising two flanges and a web and elemental length delta z of the beam as shown in figure. Now at section Z of the beam is subjected to a positive bending moment mx and a positive shear force sy, so that you can able to see in the diagram. So whatever the directions that sy and mx are depicted here, so they are the positive in the directions. Now the bending moment resultants pz1 and pz2. Now here we resolved the forces p1 and p2 into two components. So whereas pz1 and pz2 are responsible for the bending, so the bending moment resultants pz1 and pz2 are parallel to the z-axis of the beam, and for a beam in which the flanges are assumed to resist all the direct stresses, and we can write this pz1 that is equals to mx by h, and we can write pz2 equals to minus mx by h, where mx is nothing but the moment. And pz1 and pz2 are the components in the z direction of the axial loads p1 and p2 in the flanges, and these have components py1 and py2 which are parallel to the y-axis, and so that we can write from this diagram these components py1 and py2 are parallel to the y-axis, and they are given by, when you look at this diagram and if you try to write this, and if you consider the similar triangles, and if you consider this triangle as well as this one, these two triangles if you try to consider, so this is nothing but py1 and alpha 1 angle you consider, and this is nothing but delta z, and again this is delta y1. Okay, so if you try to write from the similar triangles, what you can write here, it is py1 from the smaller triangle. If you write py1 divided by what we got, pz1, okay, a vertical component divided by horizontal component, so that here also from this diagram you can write vertical component divided by horizontal component, that is delta y1 by delta z. So from these two you can write py1 that is equals to pz1 into delta y1 by delta z, so that we are writing from the similar triangles. Okay, similarly on the lower flange also you can consider these two triangles, and then you can try to write the relationship between the loads as well as the distances over here, and here also you are going to get the similar expression, that is py2 is equals to minus pz2 into delta y2 by delta z2, and we got minus sign over here because the load py2 vertical component is acting in the downward direction, so that's why we considered negative for this equation. Okay, so yeah, delta y2 is negative, that is here we got delta y2 that is below the z-axis, in which you can consider that as negative taper. Okay, and therefore the axial load in the flange, that is p1 if you try to consider, and if you consider this right angle triangle, so it is nothing but square root of py1 square. Using Pythagoras theorem you can write py1 square plus again you can write pz1 square. Okay, so that is the axial load in the flange, p1 equals to py1 square plus pz1 square under root. Okay, so again if you try to substitute for py1 from here, if you substitute py1 over here, and you can rewrite that equation as p1 equals to pz1 into delta z square plus delta y1 square whole to the power of 1 by 2 divided by delta z. And now here we are writing pz1, and then looking at this one from this first triangle here, and if you try to write what is cos alpha 1, so cos alpha 1 equals to adjacent side, that is nothing but pz1 divided by and hypotenuse, which is nothing but the square of these two, so you can write square of py1 square plus pz1 square. Okay, so this is cos alpha 1. So similarly here you are having here either in terms of distances also you can write this cos alpha 1. So cos alpha 1 you can write in terms of the displacement for this diagram, because this is again this is cos alpha 1. So you are going to get this as delta z divided by square root of delta y1 square plus delta z square whole to the power of 1 by 2. Okay, so cos alpha 1 from this diagram. Now here similarly it is looking like cos alpha 1, and therefore replacing this value by cos alpha 1. So you get P1 equals to PZ1 by cos alpha 1. Okay. So in the similar manner, you can write even P2 also, axial load in flange 2, that it can be written as P2 equals to PZ2 divided by cos alpha 2. Okay. Now the internal shear force Sy, if you look at in the diagram, the internal shear force Sy, it comprises of different forces. Okay. So let's look into that. So the internal shear force Sy comprises the resultant SYW of the web shear flows together with the vertical components of P1 and P2. So thus we can write Sy as SYW, which is nothing but the web shear flow, and then the components of vertical components. So Py1 is acting in upward direction, so you can take plus Py1, and Py2 is acting in the downward direction, you can take minus Py2. So rewriting that equation, we got Sy equals to SYW plus Py1 minus Py2. And from here again you can substitute for Py1 and Py2. We know that from the previous equation, that is Py1, that is equals to Pz1 into delta y1 by delta z, and Py2 equals to minus Pz2 into delta y2 by delta z. So that if you try to substitute here, then you are going to get Sy equals to SYW plus Pz1 into delta y1 by delta z plus Pz2 into delta y2 by delta z. But what we want from here is nothing but the web shear flow. That is what we are looking for. So the web shear flow is equals to Sy. So you can write this and Sy minus Pz1 into delta y1 by delta z minus Pz2 into delta y2 by delta z. So this is nothing but web shear flow, and this we are going to use, and we substitute in place of Sy. Instead of Sy, what you substitute for shear flow distribution formula, instead of Sy, you are going to substitute SYW because of web shear flow. Okay, because of this tapered wing spar. So now the above equation may be used to determine the shear flow distribution in the web, and for a completely idealized beam, the web shear flow is constant through the depth of the beam and is given by SYW by H. So for a beam in which the web is fully effective in resisting direct stresses, and the web shear flow distribution is found using the equation in which Sy is replaced by SYW, and which would simplify to given here. So QS, the shear flow distribution, well-known shear flow distribution problem, and that is given by minus SYW. So what we have done here, instead of Sy, we replaced SYW. SYW, that is divided by Ixx integral 0 to s Td into Yds plus B1Y1. Okay, or you can write in other words, Qs equals to minus SYW divided by Ixx integral 0 to s Td into Yds plus B2Y2. Okay, but remember here that SYW is nothing but you have to substitute SYW equals to Sy minus Pz1 into delta y1 by delta z minus Pz2 into delta y2 by delta z. So this is what we need to consider here. Okay, right? So that's all from this today's class of the introduction. What we had here, that is nothing but the wing spars and the box beams. Through the analysis we have seen. So in the next class, next lecture, we are going to see the problem that is corresponding to the tapered wing spar. So thank you everyone for watching.